things that fly: boomerangs, helicopters, and aircraft.
I'd like to begin by talking about one thing that's a little off the track. It's a great pleasure to have Robert Kroll here tonight. Robert Kroll is Australian and world champion boomerang thrower, and I did note him about half an hour ago or so. He was here, and so I've incorporated him into the lecture, and he's agreed to answer some questions at the end, more about the real side of boomerang throwing that you're going to hear from me. So welcome, and I also would like to thank Ralph Sinclair, who's been coming here for more years than he and I can remember, and he's the one who's arranged that Robert Kroll came tonight, so thank you. There was a visitor to Australia, Hungarian, called George Mieke, and he wrote a book called Boomerang. This is the frontispiece of somebody who clearly knows nothing about boomerang throwing, so I couldn't resist the frontispiece. I've actually got it here under false pretenses. I must tell you at the outset so I don't feel too good speaking. The reason that I like the subject of boomerangs, apart from its intrinsic interest and its anthropological interest, is that it integrates virtually the whole of classical mechanics into one, it brings into focus the whole of classical mechanics, and that is needed to understand how boomerangs work and how they come back and how they fly. And so it's a pretext for giving you a course in classical mechanics tonight from one end to the other. But it's not for a regular course. It turns out that boomerangs essentially depend on four effects, which all have their place in Newtonian mechanics. And each one of these effects is anti-intuitive. I mean, obviously, individually, the four effects, which I'm going to come to during the evening, each one violates intuition. And yet, of course, they have to, because further thought that you could throw something and it would come back. And so that also violates intuition in the first place. So we're in good territory. Now, let me just give you a quick view of Newtonian mechanics and why it's very important. It really began with geometry, particularly Euclid, and a more recent person, Stephen, also who brought algebra to Europe. And these combined into the geometry of Descartes, and then Newton invented and so did Leibniz calculus. And this actually had been predeceased as there was already the ideas of calculus had gone were prior in the mind of Archimedes at least 2,000 years prior to that. And Archimedes was the person who could look at a sphere or look at the surface of a sphere and say the surface area is 4 pi r squared, including our calculus. And that takes a certain ingenuity to be able to do that. And then there were inputs from astronomy, inputs from navigation. Astronomy had the effect that we had to include gravity. Navigation raised the question of why do we have tides, and clocks had to be improved for navigation. There were lots of practical arts, building and architecture, and that input the ideas of statics. And then you have this grand edifice put together by Newton, Galileo, and Hooke. And quite frankly, civilizations we know didn't had it not been produced. Now we're going to bring the force of all this to bear on tonight's subject. And just to remind you, Newton was able to encapsulate the laws into three laws. Body continues in a straight line with constant velocity that's taken on by a force. This is the quantitative version of it. The force is equal to the mass times acceleration, and action equals reaction. Now you've had the theoretical. I want to talk a little bit about actual boomerangs. There have been some very beautiful anthropological studies of boomerangs and classifications of them. And this is a picture of various boomerangs found in Australia in various areas. these boomerangs, and these are returning boomerangs. And thanks to Robert Kroll, here is an example, a genuine Aboriginal returning boomerang here, and you can see the basic features of this. It consists of two wings connected together, and these are genuine wings. If you look at them, look at it side on, I hope you can see, there's a flat side. This side is flat, and this side is curved. So it's like an aircraft wing. It has a flat underneath and a curved top. They're two genuine wings connected together, and that's important. So that's those wings. There are other boomerangs. For example, these ones at the top, which are straighter, of which there is another example. Again, thank you, Robert Kroll. This is a non-returning boomerang. There are uses for non-returning boomerangs too. Things like they actually use them for chopping and very simple direct tasks of that sort. But the fundamental reason that this will not return is because it's unstable. It needs to occupy. This is too straight. It's more like a line than something that occupies a plane. This occupies a plane, and this is too much like a stick. And it needs to, we'll discover later on, it needs to occupy a piece of plane to fill it, not just along the line like this, but actually occupied like that to be stable when it's thrown. But this has the right features, a flat side, a curved side, so it still will not return. There are other boomerangs from other parts of the world, which are crossed sticks, and I will personally be throwing this one later on tonight. This consists of two rulers joined with rubber bands, and you can make your own, and they're very good. This is based on this general design here. Now, I think before we go any further, I'd like to ask Robert if you could just stand up and show the basic throwing position of boomerangs. I've drawn a picture here, but no point showing the picture when you've got the person. Here's this.
When you actually throw the boomerang, one of the most important things is the grip. When you have the boomerang in your hand, the bigger the boomerang, the better the grip you need. So a boomerang the size of this, I'd have two fingers around it. You wrap your thumb over the top. You try and have the boomerang arm along the plane of your arm. And when you throw it, you have the boomerang on an angle. You never have it too straight or very flat. Because if you throw the boomerang flat, it tends to go straight up in the air and come down and break. So when you throw it, you bring the boomerang back over your shoulder, and you would throw it and snap your wrist forward like that, and then the boomerang would leave your hand, and you try and get the boomerang to go out on a straight plane. You don't twist your wrist at all as you throw it, it's just snap straight over past your ear, like that.
The other thing we didn't play out, I just want to play out, is the curved side is towards your cheek. It's very important that that's the case, and the flat side is away. If you're the other kind of person, you still have the curved side. The curved side to your cheek. Okay. So those are the important facts about it. Now I want to attempt to give you a picture of the flight of the boomerang. To try and describe it without any theory. It's not a very accurate picture of how they fly. But here is a picture. Now, you can look at the picture and I'll have a go at describing it. Imagine a point way down below the surface of the ground. And then coming out from this point, coming up, is a big cone coming up like this. And it intersects the ground in a circle somewhere in front of you, and you're standing on this circle when you throw it. This is a fictitious cone, it doesn't exist, but it's worth imagining it in your mind. And then what you do is you're standing, this cone, piece of the cone is coming up here, the other side's coming up there in front of you, and you stand there, and this is the boomerang is in the surface of this cone. In the surface of the cone, like that, it's tilted over like that. And when you throw it, However, the boomerang goes around in a circle, which you can think of as being in the surface of this cone. So you can see the circle going around in the cone. These diagrams are all in the lecture, by the way, so you don't have to copy. And there's one other thing that's very important. It's not just, I'm going to show you how the boomerang could go around in a circle, but doesn't go around in a circle. Forget the fact it's spinning. It could go around like this. Notice, I'm trying to walk around in a circle, and the boomerang, the plane of the boomerang is pointing at right angles to that wall the whole time. That's not what it does. It's not what it does. I'm going around in a circle. It does go around in a circle. What the boomerang does is, of course, it's turning over, but the axis of the rotation of the boomerang that sticks up here is going around like this, and it's pointing. You can see I've tried to draw a dotted line pointing to some point on the axis of that cone as it goes around. The axis of spin of the boomerang is pointing to this great point, the fictitious point up there, and it's turning around as it goes. It doesn't maintain its aspect. And that's very critical to have the thing turn around like that, and that motion is called precession. And we have to explain where that comes from. Now, so that's just a description of the motion of the boomerang, and maybe you've got a little one that doesn't take eyes out, and you could throw that one, just to give a demonstration of a little, this is a three-wing boomerang.
It's actually made of foam, so it doesn't actually kill anyone. Just give you an idea.
Okay. So that's very nice. So that you can see it happen. And now that's the basic motion, and it's very useful to have that in your head. Now the other thing about a boomerang is that whatever else is true about it, it's also an unpowered helicopter. It is an object which is actually flying. It is not just like a brick which is thrown and it makes a path. It actually is got aerodynamic lift. It's lifting in the air. It's holding itself up like a helicopter holds itself up, except whilst the helicopter has a motor to keep the thing going, this thing, you put it in with the action of the wrist that you mentioned before, and that keeps the thing going. And of course that eventually runs out, unlike the helicopter, but usually comes back before that's run out. Now, here is a picture of the boomerang in a bit more detail, and this is, I've tried to draw the view standing behind the thrower, if you like. You're standing behind the thrower, and this is meant to be this kind of a picture where the boomerang is, you can see just the line at the edge of the boomerang there, and there's a vertical line that goes upwards, and there's a spin axis which goes at right angles to the boomerang, so you spin it out there. Now, the boomerang is applied because there is a force that is holding it up in this direction against gravity. It doesn't fall to the ground like a rock does. So it's being held up against gravity. Gravity is pulling down, and there's a force coming up. And there is another force in the horizontal direction, which is pulling the thing around in a circle. And that's one of the first topics I want to talk about. This is a picture of the thing from above. I tried to draw the thrower and the boomerang going around in this section of the cone. Imagine this cone coming up. Here's the circle going around it, and there's a force pulling it towards the center. Now, the first thing that I want to talk about is going back to Newton. Now, before Newton, particularly in the hands of Aristotle, people really believed that if you wanted something to go around in a circle, you had to shove it around in a circle. You had to actually push the thing around in a circle along. And it turns out that several people, but Newton most notably, woke up to the fact that this is absolutely wrong. And they get 0 out of 10, you see, for people who believe that that's the way it works. Now, you don't push the thing roundwards. What you do is you pull it inwards. And the effect of pulling make it go round in a circle. And we'll talk about that in a moment. Now, Newton really understood this and applied it to the problem of planetary motion or satellite motion. And here is an example. Imagine the Earth with a vertebrate mountain on it, just to make life simple. I put in a big one. And imagine you're standing on the mountain and you're throwing something to the ground. And here it's throwing something to the ground, it's throwing up the ground. And then, because we don't live on a flat Earth, we live around Earth, if you threw it a bit harder, it would go around and plunk on the ground around there. And Newton was able to see in his own mind that if you threw it just at the right rate, so that it kept falling at a rate which the curvature of the Earth was ducking below it all the time at the same rate, the thing would never actually hit the ground and would keep going. Okay, so that was the fundamental picture, and that's great insight to understand that. Once he understood that that's what was going on, that there was just ordinary falling involved, then had to realise what you had to ask, what was the force pulling it in? And of course, in that case, it was the force of gravity. Let me give you an example. Here is the moon going around the Earth. I'll put it rather close. And we imagine a space traveller going past at the same rate as the moon is going, the same velocity as the moon. And you ask, what does the space traveller think the moon's doing? And the answer is, they see they're going along here, and they see the moon is over here, and it's getting closer to them. They're going along, gets a certain distance, and then it moves away again. And it's exactly, from this person's point of view, like throwing a ball up in the air. The circular motion is no different from throwing a ball up in the air, viewed from the point of view of a space traveller just going past at constant velocity. Newton understood this and actually calculated the rate of fall of a ball and calculated the rate of fall of a moon from the same diagram, and figured out that the law of gravity had to go as an inverse square from that. And here are various expressions here in the notes, etc., for the acceleration of a okay, maybe I'll just explain a little bit. Okay. Here's motion in a circle, and at one instant the object is travelling this way, that is to say this way. A bit later it's travelling that way as it goes around in a circle, and the change in velocity is this way. It's changed from going this way to that way, which means inwards, which is towards the centre of the Earth. And that's where the force has to go, towards the centre, to change the velocity in that direction. That's what Newton adjusted. And what we demonstrated a minute ago was that the string was provided that force, didn't have to do with gravity, but pulled the thing in. Now, the next thing we need to do is to work out where does the force on the boomerang come from that's causing it to fly, on one hand lifted against gravity, and at the same time causes it to be pulled inward, which makes it go around in a circle. We need two things. The thing is flipping over like this, and it has a force that's holding up in the air, and a force that's pulling it that way towards the centre of some circle. Now, what actually is happening is there is a single force which points along the axis of the spinning boomerang. We'll come back to that axis in a minute. It's pointing along that axis, and a piece of that force holds the thing up, and the other piece of the force holds it towards the centre. It's only one force, and you can adjust the various amounts of those by altering the tilt on the boomerang. If you do it this way, it's only going to be that force. If you do the tilt, if you did it this way, it's only going to be the force that pulls it sideways. Now, at the risk of hitting somebody, I'll show you. I'm going to throw this horizontally across the front, and this will only have a vertical force, so it won't go out of the auxiliary toe force. Okay, and you saw it flying. And I can actually almost make it look the loop, but I didn't want to throw it that hard. And there's no doubt about it, but it where does that come from? Well, it comes from a thing called Bernoulli's principle, which is one of those totally surprising things. We had one surprising thing already. The surprising thing is not something go around a circle. You don't shove it around a circle, you pull it sideways. That's a surprise. And that was, of course, Newton's surprise. Now, this is another surprise. We imagine we have fluid going on in a tube of some sort that varies its dimensions. And the surprise is that if the tube constricts so that the fluid moves fast, so it's going to squirt through this region, that is not the region of high pressure, it's the region of low pressure. It goes the wrong way to intuition. When you ram it through a narrow hole, the pressure drops. Let me show you a couple of demonstrations of this. The first one, this is a hose that blows air, and what I'm going to do is to blow air across this tube here, and this is a full width tube here, and this is a narrow tube here. So the air is going to speed up there. Because the air is going to speed up there, it has low pressure, and it ought to suck this red fluid up here, and this will be high pressure, will be driven downward. You don't have to watch it down here, it's up there on the telly, for those that can't see it, maybe a bit small. So let me just turn on the air, we'll blow air across, and there we have it. Now, just to prove that there's no gimmick to this air is being blown this way. It doesn't matter which way. You can blow it from the other side. So let me, whoops, come on. Here, although it's not needed. And we'll put it over, we'll go the air the other way across, like this. Whoops. I don't want to jam them together. We have a little attachment to the other floor. And we're blowing now the air this way. And you'll notice that the narrow one sucks here. It does not depend on which way the air goes. And in fact, the reduction in pressure here is it goes at the square of the velocity, and it doesn't care about the sign. And this is a standard method for measuring fluid flow, the rate of fluid flow by the difference in pressure from the two sides. Here's another little gadget which is rather nice. This gadget here is a pitot tube. It's a cone object that's used to measure the velocity of aircraft, and it consists of a hole at the end which goes through. There's a hole right at the end here that goes through into this tube. There is another region around the outside, a surrounding region, which is full of little holes, and air is going to blow past this, and the air is going to blow past that, and this interior region where the air blows past is connected to this tube, this one here. And the air around the outside goes faster and has a lower pressure, and you'll see that in here. You just blow it past. This is called the pitot tube, and it's used to measure what the aircraft. So those are some simple demonstrations. I can show you some other demonstrations which are rather nice. For example, what have we done with this? Here's a nice one. We blow air out of here, and the air coming out of here is going fast. Here it is going fast. The air on the outside, around here, which is not going, very fast. Something's vibrating. Anyway, the air going fast has a low pressure, and it's holding this balloon in the jet. The balloon can't move sideways. I'll show you that more dramatically. Sorry, here it is. Going there, we've got a more dramatic thing. Now, it's really gripped. Let me show you. I'm going to tip it over sideways. It's not sitting on a jet. It's being held by a fast airstream in space. And you can see I've got it out there sideways, going like that. And that is an example that the jet of air that's in here is going at low pressure, and the ordinary air, which is not moving, is at high pressure. Exactly counterintuitive. Called the Bernoulli effect. There are some other demos I couldn't resist getting all out here. Here's two balls. The air has to be very formal. To go between the balls has to form a jet, and the effect of the fast air going between them is to pulls the balls together. Doesn't blow them apart, pulls them together. Because that's where the low pressure is there, and the air pressure on the outside is pushing them in. Other ones. We'll blow air out of here. We'll blow air out. Put it in here. A ball. Okay. They're reverse. There are all sorts of joys for things you can do. Another one just here's another one. We blow a piece of paper, we blow it, flips, picks it up. The blowing picks it up. Like that. Finally, one day your employer might say to you, I want to make a rice bubble spray, and the air going across the top here is fast, has a low pressure, and sucks up rice bubbles. So that is an example of the Bernoulli principle, well demonstrated by a number of effects. Now, you might say that's anti-intuitive. I've tried to today invent a little argument which makes it intuitive. I've tried. I know it works if you judge. But what's happening here is here's a little bit of air that is going along and it's being condensed down, has to speed up to go through a narrow region here. And in order to speed up, it needs a bigger force behind it than in front of it, or it won't speed up. So that tells you that the low pressure is in front of it. Now, when it gets through this region, it has to slow down again because it's going faster, the constriction is fast here. So it needs a high pressure in front of it and a low pressure behind it to slow it up. And that's a clear to an intuitive picture of what's going on. There are other things I should comment on about. In the old days, when we used to have fly sprays and perfume spray, that you just had a vessel, a fly spray of perfume, you had a little hand pump and pumped some air across the top of the tube. The pressure was low, used to suck up the fluid and spray. Since then, we've chosen to go to pressure packs to get rid of the atmosphere. That's a madness, absolutely madness. This is a solved technological problem, and people have to go for these hydrocarbons and these fluorocarbons. I can't believe it. Anyway, and if you believe this, I want to tell you something else. If you go out yachting, and the boat fills with water, what you've got to do is open a hole in the bottom. That's the secret. There are people who know about yachting. Anybody here's a yachtsman? Yachtswoman in the audience? They know for a fact that you open the bottom to get the boat there. Well, what's going on here is my attempt to draw a yacht. And what's going on is the fluid is going underneath the yacht. It's speeding up to get under. And it has a low pressure here, so you push the little flap down, very low pressure, and it sucks the water out of the yacht. And when it's sucked it out, it slurps, violently slurps, makes a very rude sound. Okay, so this is another use of the Bernoulli. Now, how does that affect wind? Well, when you have a wing with a rounded cross-section, like this boomerang has, or even like this ruler has, when the air blows across here, it has to speed up to go across the top because it's rounded and it has further to go. So here I've tried to draw the picture. And the air that goes under the flat side can go more or less straight across. And so the air going underneath is actually going slower than the air on top. The air on top, therefore, has a low pressure and it's actually upwards. And so the wing is lifted by the Bernoulli. Now, it's possible, and this is relevant to tonight's lecture, although I don't care whether you understand the mathematics or not, you can say to yourself, let's think of a formula for writing out what the force of lift on a wing must be. And you'll say, well, it's going to depend on the length of the wing. If I double the length of the wing, it's going to be double the amount of lift. It's going to depend on the velocity of the air, it's going to depend on the density of the air, and it's going to depend on the width of the wing. And there's a fudge factor, which I haven't got a clue, is K, which is here, right? K, fudge factor. And so you say to yourself, if this formula is to be true, what I'm not allowed to have in physics is I'm not allowed to have in physics a formula which says on one side of the equation it says kilograms, and on the other side it says meters. You can never have kilograms equals meters. This is a no-no in physics. When you have a physics formula, if there's kilograms on this side, it's going to say kilograms on that side. If it's going to say meters on this side, it's going to say meters on that side. Now, if you check the units of all these things, it turns out by a miracle that the formula is determined by that requirement alone, that we get the correct units. And you don't have to die doing vast amounts of hydrodynamics to work out the details of the force. You can actually nut it out. And the relevant point is the following, and that's important for tonight's talk, is that the force on the lift goes as the square of the velocity of air across the wing. Now let me explain what that means in a non-mathematician. If I have a wing, and the air is going across it at 1 meter per second, we will lift it with a certain force. If we double the wind speed, so we go 2 meters a second across here, it's going to have 4 times the lift. If we go 3 times across, it has 3 by 3, 9 times the lift. So it goes as the square of the velocity across the wing. That's very, very important. Just before we look at that, I want to show you some picture. These are 2 actual pictures. This picture is a picture of smoke trails going over an actual wing, and you can see them having the curve on this side and so on. And this thing is a picture, actual data, taken from an actual wing. The wing is covered in little pinholes that go from the inside. The wing's hollow, and there's a little pinhole in the inside. It goes from the inside to the outside, and there's a tube connected to that pinhole, and that goes off to a pressure gauge. And so at the tip of each of these arrows on an actual wing, there was a pressure gauge, and the length of this arrow tells you what the pressure was measured in at that pinhole. And what you can see is that the high pressure, because of these long arrows at the bottom, was below, and the low pressure was on top. And that's actually determined. This is actual data determined on a particular wing. Here, just the last thing is the force of lift is proportional to the length and goes as the square of the velocity of the air over the wing. Now, we have one more problem. Here's the problem. Here is what I want to go back to something I said before and try and describe the motion of the boomerang again. I want to describe it first of all what it doesn't do. It's important to know what it doesn't do to compare it to what it does do. This thing is spinning like crazy, like this. It's two-sided like that. And what it doesn't do is go around in a circle like this, maintaining its attitude. Although it's spinning, it doesn't maintain that plane. What it does is the plane goes around. The plane in which it's spinning goes around to lie more or less inside that big cone that I had drawn there before. More or less like that. Okay, now the question is, why does it turn? And that is a precession, and it is a property of rotating bodies. And I want to do a couple of demonstrations of properties of rotating bodies to show you a particular effect. Here's a body that's not yet rotating. And I hang it up by a string, and you can see under gravity it just dangles. Okay, it just dangles. If we speed it up and make it rotate, and I can put my we'll make this thing rotate reasonably fast. This object will not dangle, but you'll notice I am pulling it upwards on this end, and gravity was pulling it downwards there. And so this object, if I grab it for a minute, there is an attempt to, by me pulling up on the string, and by gravity pulling it down, to twist the thing like that, around this axis. See, this could come up and that come down, but it doesn't do that. It moves at right angles to that. It moves at right angles to the way we're trying to twist it. And that is very, very anti-intuitive that it should do that, and that comes out of Newton's equations of motion. Well, that is the precession effect of the gyro. I can show you a little bit more simply on this gyro. Let me just do this one up. This is just a motorized reel in here that's spinning. And before it's spanned, it's on gimbals that can go in any direction. If we put a weight on the end of it, so as we pull that end down, the thing moves at right angles to the way that the weight is trying to pull it. The weight is trying to pull it down, and it chooses to move that way. And the more weight, the faster it goes. I can put more weight, and it will go faster. It will go around faster, but it will not drop. And this object, this gyroscopic motion, which I demonstrated with the bicycle a minute ago, that is the thing that is causing the spin axis to do this. So the question now is, where does that come from? Where do we get the twisting motion to do it? Okay, let's go back to the boomerang and imagine we're throwing it now again. The boomerang, hold it this way, okay? You're going to throw it and spin it. Now, there's two motions of the boomerang, and watch. Maybe it's a little better if I do it with the ruler. Maybe it's even simpler with the ruler. Okay, so here we have this thing that has four wings, not like this one has two. And it's doing two motions. Watch the two motions. One of them is it's just going along like that. I'm just throwing it so it goes forward. The other motion is that it's spinning. It's doing the two things. And now watch what happens when the two things happen together. First, watch the top of the boomerang. The top part, whatever wing is at the top, watch that. It's going forward because I threw it forward, and it's going forward because I spun it forward. And so it has a huge velocity forward for two reasons. The bottom of the boomerang is going forward because I threw it forward, but it's going backwards because I spun it backwards. So it's a spinning motion. It's subtracting from the forward motion of the throw. It's subtracting the velocity of the bottom wing, whatever wing is at the bottom of the boomerang. Now, we learned that the force of lift on a wing goes with the square of the velocity. So if this wing at the top is going twice as fast through the air as the bottom one, this is being lifted 4 times on the top there, and this wing is being lifted 1 unit of lift. Both units of lift are lifting the wing that way. That's what's holding it up. At the right angle, that force up there is what's holding it up. It's got a big force on the top, little force on the bottom. That's holding it up. And part of that force is holding up against gravity, and part of that force is shoving it towards the center of a circle, which is why it goes around in a circle. But as the force is greater on the top here than the bottom, it is trying to do this. It's spinning around there, and it's trying to do that. But we learned that the thing doesn't tilt that way, it tilts that way. That's what this shows. It goes in the right angle direction to the way you think you shoved it. And so let's just go through this again. It's spinning around, here's the spin axis out here, it's spinning around that axis. There is a big force trying to push this wing up here, a little force that's doing nothing much to this wing, and so it's trying to tip over, but it doesn't tip over, it does that instead. It goes at the right angle. So that's what this wheel did, that's what this thing did, and that is what is making it go around. As it goes around, it's facing inwards the whole way. Facing inwards the whole way, because it's precessing. And it's the job of the thrower to match the rate of turning of the boomerang through precession with the force Well, this is, I think I've explained it enough with my fingers and actual objects, but this is an attempt to draw what's going on. The boomerang is going thrown this way, the top is going this way, it's got a lot of velocity, it's a big lift, this side is small. And here is a picture in diagram form of the gyro that we saw, which is a spinning object. We put a weight here, and from the top it goes around in a circle. It doesn't, it goes inward. It's pulling it downward, but it goes inward. And here it is looked at from on top. That's this object here. I attempted to explain this. People always want to know, why does it actually do this? Is there an intuitive way? And I've got an attempt here at why a wheel does do this precession. The reason it does this precession is because here's the flywheel rotating, and we pull this side up and that side down. And forget the fact that there's now a rotating wheel for a minute. If I have a bar going through another hunk of metal there, and I do that, then you see that this constitutes a lever which is shoving a little bit of matter which I call a sideways. It's shoving it sideways. You see that if I just grab a force here, think about what's happening to this bit of particle up the top there. If I go like that, this gets pushed sideways. So this force here and that force there, through the metal, put a force on a piece of the metal sideways. Now let's look what happens on top. Here is the sideways force, applied to a piece of metal which is trying to go in the direction which the rotor is spinning. It's trying to go straight across the top, but it's being shoved sideways. So it swings in an orbit like that, and of course the way that happens is for the wheel to turn like that while it's rotating. And that's why it goes at right angles to the direction of the torque. If you think directly what a fragment of matter is doing on the top of the thing, you realize it's being swung into a path like this. The only way you can get a path like that is for the rotor to tilt around that way so that the metal doesn't leave the metal of the rotor. So that is my attempt at explaining that. Now, there's one other aspect that I want to talk about before we leave, and that is to do with the stability of rotation. That is, now we understand, I think, the basic motion. There's a force pulling around in the circle. There's a precession which is tilting the plane around, which comes from the differential lift on the various blades. And there's this force that's also holding up in the air, which causes it to fly, and another sideways force that makes the circle. So those are the ingredients. They come from the three effects. The force at right angle makes something go in a circle. The fast air makes low pressure, which gives you lift on wings. And this precession, which causes things to apparently move, not apparently, actually move right angles to the way they're shoved. Now, vast amounts of mathematics later, which I'm skipping, but it's in the notes for those that paint themselves. Stability of bodies. Now, here is this actually is a frisbee, and I'd like to say Steve Damon, who's responsible for a nice demonstration, I'd like to thank him now for the demonstration. This is a frisbee that he supplied me, but I used a plastic plate because I couldn't find a frisbee last time I gave it to him. And so this I want to describe plastic plates and things when you throw them. Now, if you take a flat object and throw it, you'll notice that I spun it when I threw it, and it stayed in a plane. It stayed in its plane. It didn't come out of that plane. It stayed in a plane pretty well the whole time. Now, the question is, that indicates there's something stable about the rotating body. And I'm going to now spin it up and give it a bit of a flip when I do it, and I want you to watch the motion now. Whoops, excuse me. Again, I want to give it a little bit of a wobble as we, I hope you can see it wobbling. Wait, that was not enough wobble. It's wobbling as I spun it. It goes around and it wobbles. It's sort of go like this as it's going around. Now, when you see something wobble, that's always good news for the following reason. That it tells you that this thing starts to go away from the motion you wished it had. but it goes back again. And this is a sign of stability. Whenever you have an object which wobbles about a position, you know it's intrinsically stable because it's hunting for the right position. It is physically what you hunt. Okay? It didn't flip over like this. Now, I don't want to ruin this object, but if we tried to throw this boomerang, it would not go around in a plane. This would not go around in a plane. It would when I just started throwing it, and then all of a sudden it tumbled chaotically in a very complicated thing because it hasn't got features. It is not, this, if you like, this object lies in a plane. It lies in the top of the table. This thing is too stick-like, and I can roll it like this too easily. This is hard to roll. This is a hard object to roll because it's got a lot of width in this direction. And these objects are quite flat. Frisbee is quite flat. And so they have this feature of stability. Now, the stability of rotating objects about an axis which is right angles to a surface, a planar surface, has been prediscovered by nature. And I wanted to just give a little demonstration of that here. You will see it first, you know, it's published in real time, and this will actually be the conclusion of the lecture. Here I just put some light up so you can see what we're looking at. And these are sycamore seeds. And I want you to watch firstly selected from the botanical garden. Now, here's one sycamore seed. I'll drop a few in a minute. I'll put it in the light. And it's going to dive bomb for a minute, and then it will realise that's the wrong way to do business, and it breaks into goes into flat motion, tips itself on its side, turns itself into a wing, and flies. Of course, nature had to discover that because it wants sycamore seeds a long way away. And so we can drop a few more. And there we have sycamore seeds. So some of this has been discovered by nature. I think we'll end at that point. I'm happy to answer questions now. I believe Robert's got the answer too. Thank you. Now, I understand what you're on about, because this wing eventually goes down there. But when you do it, you can average the twisting force over the entire rev. In the case of this four-wing one, as soon as this wing gets out of the way, there's another one coming up to take over. Even that's true of the regular boomerang. It's spinning about its centre of mass, which is sort of here somewhere. And just as this wing gets out of the way, the other one comes up, and they interchange their role. Actually, I didn't actually do a nice throw of this one. I want to actually describe it. I'm going to throw this one across like this, and this one will spin like that, which means that this side is going to be lifted up. That's the side that's going to be lifted. I throw it horizontally like that. So it's going forward, it's spinning, this is the side that's going to lift it. So it's trying to turn that way, yes. But the axis of spin is this way, pointing upwards. You use your right hand, it's spinning around like my fingers, and the axis like that. And the torque, then you see the force is like that, so it's tipping it back there. So the force, there's a spike picking up there with the rotation, it torque is pointing backwards, and therefore this will hit that way. Watch. It actually will have, but please watch out if I misfire. So shelter your eyes. Oh, swung up, that's what I was trying to show you. And it did that. Swung upwards. And notice all that motion, while I just threw it somewhat, I didn't cause it to go basically sideways. It goes upwards. After all that motion, imbalance movement. The reason I move this out of the way, this is really what's causing the trouble. Okay, the high kick here. Let's say this, the Earth's spinning about a certain axis, but the axis is also wobbling around. That is it's the same physics, because the precession of this axis is the same physics. Yes?
Professor Opat, what would happen if you gave the boomerang the usual track one we're talking about, the development later on, it gave a perpendicular, fairly high speed velocity straight up, what would happen to that? What would have to do it then?
It would just be a flat piece of wood thrown upwards. I mean, it wouldn't do anything special. It wouldn't fly. It would just be, the air resistance would be against it. It wouldn't have any stability because it's not rotating. It wouldn't precess. It would just be an uninteresting motion. Or we would do it. I mean, I'll do it with this. So,
No, I mean the spinning force
with
as
a
well.
spin,
With the spinning force as well.
with a spin, it can. If it's flat enough to lift like a helicopter. Yeah. You want to talk about actual throwing, maybe?
You mean if you threw it straight up like that?
No.
I mean, close it.
Okay.
The usual boomerang was probably, I think, before 1700 in Australia, I think the Aboriginal Australians only had a boomerang that could kill a kangaroo and didn't come back. I think it's a fairly empirical fact. And if you gave it a great force like that, and straight up, what would happen?
I think it would just spun.
It's got to go perpendicular.
Straight up like a helicopter.
Well, I can
No one's experimented.
actually I have a boomerang here. This is actually a boomerang I use in competition, and it's used to stay in the air a long time. Now, a general boomerang will stay in the air, say, one like this, no matter how hard you throw it, probably 10, if you really have a good arm, maybe 15 seconds. Now, you throw it as hard as you can, it goes around a circle and hovers, comes down, you catch it. Now, this boomerang here, this boomerang could stay in the air theoretically forever. It's actually never slows down, it spins, and if you get a thermal, which you do get quite often, the boomerang will actually go up, it won't come down. So what happens is, the boomerang, once it gets into a plane like this, will actually just go straight up. And I've had friends lose these boomerangs straight up going, oh my God, thinking, when are we going to get this thing back? And it just disappeared out of sight, and half an hour later he's still standing there going, where do I go? So, these boomerangs are actually thrown like that, where it's not dead straight up, but you throw them very high, similar to how you would throw serve with a tennis racket. You bring it right up over like that, and the boomerang goes very high, and as it turns, it spirals up and then it actually hovers like that very, very high. Then if you get an updraft, I've had cases where they just hover around. The longest time that someone's thrown and caught one of these type of boomerangs is 18 minutes. And the chap actually ran 400 metres in one direction and wind changed direction. Just as he got to a river, he was about to jump. And the boomerang went, oh, hang on, I'll come back. So he ran back. The boomerang went 500 metres in the other direction. He ran back past where he'd thrown it. He ran 100 metres past where he threw it. The wind changed direction again and came back. He caught it 42 metres from where he originally threw it, 18 minutes after he threw it. So they can actually stay in the air a long time, and they can actually, it's very difficult to just spin a boomerang and have it go straight up, but if you get an updraft, that gives the boomerang a force to sit on, and these boomerangs actually sit in like a dish type plane, and they can get to the stage where they're so stable, I'll just go straight up.
Do they keep spinning?
Yeah, these things will never stop spinning. If I could get one of these, the same sort of force with the air, and have it spinning, it would just sit there spinning. And you'd have to have the right sort of forces on it there. And like theoretically, it could never come down. But if you tried it with, say this one, the forces on this boomerang, there's too much drag because it rotates around a point very close to the centre of the boomerang, and the boomerang tends to slow down and it would just run out of spin and drop to the ground. Whereas this boomerang, when it sits in a plane, the centre of the axis of the boomerang tends to be down the arm a bit, and that makes the boomerang rotate around a point more like that, and the boomerang has very little drag. And it also has bending it like that, and also has a twist, has a negative twist on this arm, a positive twist on that arm, and all that combined gets the boomerang to sit stable. It's actually very difficult to get a boomerang, what we call tuned in the right direction, to actually stay in the air a long time.
From a practical point of view, using a boomerang as a weapon, something like that, on a windy day, should you throw it so that it's, let's say the wind's going from the right to the left, should you spin it in a clockwise direction, or should you spin it in an anti-clockwise direction?
Well, say like if you're talking about hunting boomerang, there's really only one way if you're right-handed that you can throw the boomerang with any great amount of force. I mean, you can throw it backhand, but you can't get the same amount of force as you can throwing it this way. It generally depends on what the boomerang is shaped like as to the way you would throw it. A boomerang like this would work best thrown in this direction because of the angles that are on the boomerang. If you throw it back the other way, it tend to just drop into the ground more than it would to fly in a straight line. Also, if you've got a left-handed boomerang, you need to have a boomerang shaped opposite, like a mirror image of a right-handed boomerang. So it wouldn't matter which way the wind was going with a boomerang, it doesn't come back, you would just throw it the way you would normally throw it and not worry too much about the wind. Also, these things are very heavy and they're made that way so that when you hit something, it doesn't just go, oh, what was that? It goes, I'll be your dinner. So.
Okay. All right. Well, I'm sure Geoff would be happy to answer his question.
Would you please have a demonstration of the boomerang fly up over the back row and actually punch that?
Let's say boomerang.
Well, I'd probably take some of it off. I mean, I can throw this.
The other one. Yellow. It doesn't go very far. No.
Maybe I can just demonstrate the boomerang like that. That would be
That's a big one.
Okay, well, as I said before, I'm sure Geoff would always be happy to answer any questions you might have over a cup of tea or coffee that we have outside. Now, before we all go, there's a few thank yous. Firstly, I'd like to thank all of you for coming along to this year's series. It's always great to see so many people coming out to listen to popular talks about physics, and we look forward to seeing you all again next year. I'd also like to thank Steve Damon, who's behind the video camera up the back, who's been behind all of these demonstrations that you've been seeing over the past few weeks. And if we could just give him a also, before I forget, Geoff has made copies of his overhead transparency that just to cover the cost of photocopying, we charge $2 for. There's also extra copies of the overheads from my lecture last week and David Jamison's from 3 weeks ago. And just